So in this section, we will cover the classical node embedding methods, just an overview about these methods, and then we'll go into the single layer GCN and an introduction about how it works. So as we have seen in the previous session, so basically we introduced machine learning, regression problem linearity, nonlinearity, and then we explained why these machine and deep learning paradigms, they are limited because they basically adopt an individualistic approach in training, including even, like other variants and advanced variants of machine learning, where we, for example, tackle manifold learning. We also formalized deep learning as a sequential manifold learning problem where you're learning different spaces or subspaces to represent your data better. Still, even with this nice deep approach, we are limited by the independence between different training points, okay, or training samples. So the idea that we introduced at the end of the session was to kind of model or encode the interaction between different samples. So we introduced collectivist points which co-learn and co-interact via a graph structure to learn better and to kind of solve downstream tasks such as classification, regression, or multi-regression problems. So all these learning tasks can be theoretically, or like I would say, like hypothetically, at least for now, improved through graphs. And then we asked the question, okay, now that we are encoding the data onto a graph, so how can we represent the graph? How can we extract the features? So we went over basic methods or classical methods for node, edge, and graph features extractions. And these are limited because they cannot take into account what we call the edge and feature matrix and additional annotation of the graph via feature, node features, or edge features, okay? So now it's all about the features. So how can we learn to embed or to extract or represent the graphs better, get features from the graph? So as you guys remember, this lecture is about feature embedding. And now we're going to talk about these features. So how can we learn better features? And I want to take a step back and introduce this concept a little bit better. So we covered it in the first session, as I mentioned, but here let's formalize it better. So first, sample embedding. So we have a data sample. Let's call this data sample XI, okay? So it belongs to RG, it has the features. So we call sample embedding or latent hidden representation learning. We call it also sample encoding, transformation, or sample mapping onto a space, a new space. Oops, sorry. Onto a new space, and this new space will allow us to represent the data better, and this space has d prime dimensions, and if it's we want to kind of reduce the dimensionality usually, so d prime is lower than d or smaller than d, okay? So for a graph in this case, so given a graph G, we have a graph G with nodes V and edges E. So we want to encode a single node. So let's say our goal is to encode this node to learn how to represent it by learning the F mapping. So this is quite similar to manifold learning. So we're learning how to embed features, okay? So our goal is to learn this ZU, this new latent representation or embedding of node U, and this will belong to, let's write here, I'm gonna change the notations. So this belongs to RG prime, all right? So now F is called the encoding function. It maps U onto an embedding ZU, a new feature representation. And this basically is important because if we learn, as I mentioned earlier, if we learn how to represent the node better, how to extract a good representation that like kind of gets rid of the unimportant features, that captures the topology of the manifold better, the relationship between the samples better. This can boost downstream tasks like such as classification, regression, also unsupervised learning tasks such as data fusion or integration or generative learning. So all of these could be improved potentially or eventually by this embedding. So this is so important. This, representation is vital to many learning tasks. Now, if you guys can see, so here in this case, the embedding is kind of constrained. Okay, so typically in feature embedding or in shallow data embedding or graph embedding methods, so in the literature of graph embedding methods using a matrix, the adjacency matrix, we hypothesize that neighbors, nodes that are close in the graph, they should be also close in the embedding space. So this is the reductionist hypothesis that we made also, if you guys remember earlier, in manifold learning. So we want basically neighborhood preservation across the original and embedding spaces. And in this case, we want, the nodes to be close in the embedding space. So which means in this case, if my embedding space has d prime dimensions, I want these, two vectors to be close. So one way of calculating that is to do the dot product between them. So ZU transpose ZVs, this quantifies the similarity between these vectors. And our goal is actually to maintain, the similarity between U and V. So if, the similarity here between U and V is high, then this should be, close to 1 if we normalize it, okay? Cool. Now, so the objective function of graph embedding or node graph embedding, to be specific, is this function. So basically, we want to maximize over this loss. So we want to maximize the dot product or the similarity between the embeddings or the mapped, transformed, encoded pairs of nodes. And this maximization is valid only for pairs that are close or similar in the original A matrix or the graph, okay? So if two samples are actually similar, we want to kind of maximize their similarity in the embedding space. So F here, whatever F we're going to learn, the learnable F should allow us to maximize the similarity between them. So if I have, for example, UV very close in the original, space with their features, and then in the embedding space, ZU and ZV, I have, for example, for a first solution, I have an F that gives me a 0.8, and then for the second solution, I have an F, let's call it here F0. This is F1 that gives me 0.5. So maybe this is kind of better because the original similarity is close to 0.5. Okay, so we need a solution that approximates the similarity, especially for those that are very close to one another. So this is the hypothesis of neighborhood preservation. And if you guys remember in machine learning, there is this principle which states, tell me who your neighbors are. I'll tell you who you are, okay? I'll tell you who you are. And this is, the neighborhood preservation, because if I know that this node, for example, is close to these two nodes, and these two nodes have the same label, so I would hypothesize, or I would, think that this node would share the same label. Okay, so this is, something that is very important. This principle is very important. And now let's move next. So this is simple graph node embedding. So basically, you take now a node in the graph V, and you encode it, and you can define ZV here for this particular node. And this embedding belongs to, RG prime. And this is actually the whole embedding matrix that is called Z. Okay, so that's the embedding matrix for all nodes of the graph. So here we have, here are the number of nodes. All right, so this is the number of nodes. And this is the number of, it's the embedding size, or the dimension of the embedding. Okay, cool. So now, one thing about this, so you may ask or think about the objective and how are we going to learn the F, okay? So to learn the F, So the f actually is important for us, but before we learn the f, we need, which is basically here, so f is, let me write it down, so it's f u transpose f of v. So in order for us to learn the f, we need to define the similarity. So this similarity measure, whatever we're using here, we need to predefine it. So because we want to preserve it, right? So we want to preserve this value. And for us to kind of be able to preserve this value, we need to define a similarity, how to calculate similarities between nodes, how to calculate the similarity between these two nodes, each, pair of nodes, all right? So now the question is, how are we going to do that? So there are different approaches in the literature using kernel methods, using different, ways of calculating that. But here in this example, we need to think about different ways of defining similarities and selecting or identifying the best ways, okay? So it depends on the graph, it depends on your problem, it depends on your learning task. So there isn't a universal way of doing that, but you can think about different things when you are defining similarities. So one thing is basically let's do this. So taking into account the connectedness. So you can say that, okay, so if two nodes are connected, then they are similar. If they are not connected, they're not similar. So these, two nodes are not similar because they're not connected. So it could be based on connectedness. It could be also based on shared patterns. For example, these two nodes, they share the same neighbor. So depending on the number of shared neighbors, we can argue or we can derive the similarity of these nodes. So it could be based on the local neighborhood or the local the shared neighborhoods between different points or different nodes. Okay, so another way is looking at topological rows. Like for example, we have a node right here, and these are two nodes, and these are my two nodes, I and j. We can say that these two nodes are very important. They're very similar because they have an important topological role. They're both central. So if I remove this node, I'm going to break the graph completely. If I remove this node, also I'm going to break the graph into two parts or two modules. So these nodes are vital, and you can consider them as central nodes. So these are central nodes, and because their centrality measures are very similar, I don't know, like for example, could be 0.8 for each, okay? So the centrality of I is equal to the centrality of j, so we can say that these are actually similar. So you guys can see here that there are different and multiple ways of defining similarity, and this constrains the learning and defines the setup of the whole optimization problem that we have here, which is a maximization problem, because depending on the way, sorry, so it's kind of blurry, but this depends completely on how we're going to define this similarity right here. All right, cool. Now let's look at so we're not going to explore different similarities here because this is also part of graph theory course. You can explore this a bit more. So using, for example, graphlets. So let me give you an example. So graphlets. So what is graphlets? So you can count the number of graphlets. So if you have graphs, so you have one graph that looks like this, okay, and another graph maybe that looks like this one. So here we have graph G1 and G2, and graphlet is a small graph. So let's take a pattern of a triangular pattern here. So we want to represent this graph, and we want to calculate the similarity between these two graphs. So we can define that based on the number of graphlets within this graph. So here we can find this pattern once and twice. So we have the value 2 here for this graphlet, for this mini graphlet that's called G1, okay? And then here we have 1, 2, and 3, so we have the value 3. So this shows that the structure is a bit different. We can have other types of graphlets. For example, we can have a graphlet G2, which is the number of edges, right? So it's very simple. So you just count the number of edges here. So 1, 2, 3, 4, 5, 6, 7. So you put 7 here, and here 1, 2, 3, 4, 5, 6, 7. So here, you guys can see these are a bit very problematic. So one measure tells us that these like these graphs are identical almost. And this one tells us that they are actually different, okay? So this is a bit, so the similarity here that we're going to use is very important. So what you can do is you can stack this up. So instead of having having your similarity defined by a single graphlet type pattern, you stack them up. So you define a subset of graphlets. So you have so many graphlets, G, for example, M graphlets, and then you can extract these, and you're going to have two big vectors, and you can calculate the dot product between these two vectors. And maybe that would be a better similarity measure to use to define the similarity between graphs if you want to do a graph embedding, all right? So these are just a few ideas here. But yeah, so it's a big topic. Now, let's have a small exercise together. So a true or false exercise. And I would like you guys to take a minute and think about these statements one by one. And you can pause the video and assign a false or true to each of those. So let's look at these statements one by one. So the first one states that shallow node embedding. A shallow node embedding is a task-dependent learning problem. So task-dependent, it means depends on the task that we have. For example, supervised learning tasks such as regression. So this basically means or implies that we are using the target values or the y's, the target y, to learn the embedding themselves. And if you guys look here at this formalization, our objective function is to learn an embedding function f, and this embedding function doesn't depend at all on the output label, right? We don't have any label data here. We don't need actually labels. So which means that our embedding is not task dependent. So this is actually false, okay? So we can make it, task dependent, but here in this case, it's fully unsupervised. So the second one is node embedding is unsupervised or self-supervised. So I already answered that. So it's unsupervised. It could be also self-supervised if you want to reconstruct the original data. So that's true. All right. And we utilize node labels and features for embedding. This is actually false. So we don't utilize any node features and labels for embedding. So node features here, it means our graph here has some labels. So we have a label for either the graph or the node for each node. So for node U, so we have YU. So we don't have any labels, and we don't have original features. We don't have an X, U to embed here. We're actually trying using the graph, simply the graph structure, the adjacency matrix right here of the graph. We're only using this one to get the embedding Z of a node U. So we don't have any feature matrix X where we assign features to nodes, and we don't have any labels. So these do not exist, okay? So we didn't need that to do the encoding. So this is actually a very simple problem to solve in terms of, fully unsupervised. It doesn't use any labels or any features. And that's something, these are important kind of remarks, because we will see that this is a bit reductionist. It's very oversimplistic, okay? This is why we call it a shallow node embedding, okay? So we have seen, guys, that this shallow node embedding or encoding, it doesn't take into account the features, potential features that we have on nodes. So it's very reductionist, and it's very simple. Basically, it only relies on the A, uses the A to learn the embedding function. So that's the only thing that we need to learn the encoding function f, okay? So this doesn't allow us to work on annotated graphs, on graphs with, features. Also, this is fully unsupervised. It's not connected to a downstream task, right? So this learning task is independent. And it's kind of, very simple. So if we want to do more exciting things, if we want to learn how to classify or regress, we need first to extend this to take into account labels and features, we need to kind of make this embedding more kind of representative and correlated with the final outcome that we want. So now I'm going to introduce the popular GCN network, which is a graph convolutional network, and we'll start with a simple layer. So if you guys remember at the very beginning, we had, this kind of big overview, just giving the rationale behind deep neural networks. So deep neural networks, they learn sequential transformations with some nonlinear activation layers, and these allow us to transform sequentially original features into a final feature representation in a space where everything becomes simple, okay? So it becomes, in terms of the relationship between, for example, classes, they become more separable, linearly separable. If it's a regression problem, we can fit a linear model or a linear hyperplane onto the data, all right? So now we're going to look at this and reformalize it using graphs. So let's see how turning this individualistic kind of learning into a collectivist learning via a graph structure, how can we change or update this kind of mapping function of the whole network if we were to model it, the interactions between different points using a graph.